Yep, I think we are all set up and we are good to go. Hang on a second. Yep, that's it. Hi guys, my name is Ameya Dubey and I will be presenting on skip lists and introduction. This also serves as a good first look at randomized data structures. So when you took your first course in data structures, most of them, the structures introduced to you were deterministic. You sort of had some look at probabilistic analysis when you came to quicksort perhaps, but it's pretty cursory. Skip lists heavily involves randomized analysis and it will be heavily used in this particular set of slides and it will be covered by me. So the complexity analysis part, I am presenting it, as you can see, with a colleague Siddharth Negi, and he has covered in a previous video the important points of skip lists. That is he has covered the search, insertion, deletion and the important algorithms, how they work. I will be justifying their complexities to you and rationalizing why exactly skip lists are an excellent data structure to use. So let's jump straight ahead to the complexity analysis part. Yep, so we are here. Now obviously, as you all know, it involves a discussion on both the space complexity and the time complexity. Let's start with space complexity. The average case takes order n space. This isn't very hard to see, so this part doesn't involve a lot of mathematical gymnastics. Let's say we consider a column. Now let me introduce to you what a column is. It consists of all the nodes of the same value across all lists. So take for instance a particular value and connect it across all the lists. I think Siddharth introduced you to quad nodes. So just keep going up until you hit the end, and so that's a column. So now we simply see that the expected number of nodes is equal to the sum of all expected number of nodes in column I, because they are all independent of each other, and even if they weren't, linearity of expectation clearly says that, so we don't even require the independence relationship. And in this case we see the number of nodes in a column is simply the sum, the geometric sum 1 plus p square up until p to the h, where h is the height of the skip list. And we can see that this is less than the sum of the infinite GP, which is simply 1 upon 1 minus p. So plugging this thing here, we have the space less than n by 1 minus p, which is clearly order n. This is what we are interested in, because later on we'll prove that this case holds with high probability. The worst case, on the other hand, is order n log n space. Moving on to the next slide, that was a pretty short discussion on space complexity, but now we are more interested in the time complexity, which is what makes skip lists very attractive as an option. So when we come to the time complexity, search, insertion and deletion have the same asymptotic time complexity. If you remember the algorithms, you can very clearly see that search, insertion and deletion all have somewhat similar algorithms. So in search, you clearly keep going down whenever you can, and you hit in each list, you keep searching until you hit the node that is just bigger than the current node, and then you go down. So I think the algorithm is pretty clear. You do the same thing in deletion, except you keep a list of the pointers you need to delete, and in search you just keep flipping coins. In insertion you just keep flipping coins until you get a tails. Yeah, right. So I'll make a weak claim and a strong claim. So the weak claim here is that the expected time complexity is order log n, which has been discussed by my colleague. But the stronger claim here is that the time complexity is order log n with high probability. So we're not talking about the expected time complexity here. This is an important distinction to make. Time complexity is order log n with high probability. We're going to shortly define what this means. So again, we'll define what is the meaning of with high probability. So I'm going to read from the slides here. a parameterized event E alpha occurs with high probability if for any alpha greater than equal to 1, E alpha occurs with a probability of at least 1 minus C alpha upon n to the alpha, where C alpha is a constant depending only on alpha. Let's distill this down to what it actually is. So what you hope for is this particular thing, 1 minus C alpha upon n to the alpha. This is the term we are actually looking for. So this guarantees that the event E alpha will occur with a very high probability, that is very close to 1, and the error probability, so this term here, right here, is called the error probability. So this is 1 upon polynomial in n, and alpha is something that we can decide. So E alpha is a parameterized event. So if we choose alpha, we can place a suitable bound on E alpha. Again, one very basic result from probability is being introduced here, which will be useful later on. It's Boole's inequality, and it is simply the probability of a union of some events is less than equal to the sum of the probabilities of those events happening. So this is a very intuitive result. I have written it here. As you can see, I mean, E0, E1 until Ek will have some overlap. They might have, they might not have, you never know. And in any case, it will be less than the sum. So this, in fact, is derived, I think, straight away from basic set theory. So this is pretty obvious. Now we introduce to you the height of the skip list. We claim that it is order log n with high probability. So we're going to use Boole's inequality here. So let's claim that it's the height is C log n levels. So we'll find the reverse claim. So we'll so the probability of this event E alpha is should be 1 minus C alpha upon n to the alpha. Now we take the event not E alpha, and we show that it has the probability of at most C alpha upon n to the alpha, and then we are done. It's the same thing, right? So we claim that the probability that the height is greater than C log n is less than this term right here, this term. So that's C alpha upon n to the alpha. So we use Boole's inequality. So the height is simply the height of the max column, which is n into probability of the height of any one column being C log n, greater than C log n, and we have multiplied by n because this is exactly what Boole's inequality does. So this is greater than that, and now this is simply n into half to the power C log n, because we are flipping coins and we stop flipping coins until we get a tails, so we need all heads until then. Again, doing some mathematical manipulation, we eventually arrive to 1 by n to the alpha, which is what we wanted. So we have proved that the probability of height being greater than C log n levels is 1 by n to the alpha, is less than 1 by n to the alpha. Alpha here is simply C minus 1, as you can see clearly from the derivation here. So we have cast C in terms of alpha, and so we know that for any C we have a suitable alpha, and so we have essentially proven that this result holds with high probability. So now we take a 2-level skip list, and we work on the expected time complexity. So this is in the expected case, so we are idealizing quite a bit here. So we take a 2-level skip list with levels L1 and L2. The expected search cost is L1 plus L2 upon L1, the moduli, obviously. Okay, so let me pause a bit here. We take L2 by L1 because we imagine that the list L1 is divided such that it is on equal intervals above L2. Yeah, so that gives us the best possible case. So that's the most ideal, and it's also easy to analyze. So we are going with that. So we go along the list, and So we go along all the elements of L1, and then we go along the last L2 upon L1 elements of the list L2. So that will be our time required to reach the last element in this 2-level skip list, which is simply L1 plus L upon plus n upon L1, because the last list has all the elements. We need to minimize this worst case scenario, and so it is this will be minimized. You can clearly differentiate and find the optimum. For L1 is equal to root n. So as you can see, the pattern is the search cost here, substituting root n right here, we get the search cost as 2 root n. For a 3-level list, that will be 3 root n, 3 into the cube root of n, and for a k-level list, you can probably guess the formula by now, k times the kth root of n. So now we proved in the previous slide that the height is c log n, right? So we take log and we take the base 1 by p. P here will be chosen for simplicity to be 2. So we have So we have log n base 2 level list, and we again simplify this, and we get the time complexity to be order log n, which is what we wanted. Now we'll make the proof of claim with high probability. So let's rewind a little. We made a weak claim that expected time complexity is order log n, which is what we have shown just now. Now we'll make a stronger claim that it's not just order log n in the expected case, but most of the time it's going to be order log n. So yes, we come down to this slide. We analyze the search algorithm backwards. So this is a novel idea we're going to apply to prove this result. So analyzing it backwards, we start tracing the search from the bottommost level. Again, I'm only dealing with search because as you already know, insertion and deletion are order log n. I mean, they are the same. So if we've done search, we've done them all. We start tracing search from the bottommost level, and then we go up one by one. So at each visited node we have, if the node wasn't promoted higher, that is, if we didn't get a tails, we got a tails there, right? Then we came from the left, obviously, because there's no node above it. But if the node was promoted higher, that is, we got a heads on that, then we came from above. So we keep going up, and we stop tracing if we hit the first level. So they say the height is c log n. So the number of up moves obviously can be at most c log n. So the cost now is the number of times needed to flip a coin to get c log n heads. Think about it. C log n is the height of the skip list. So the up moves can only happen when there are heads, and there are as many heads, and the heads are determined by the coin tosses, which again we saw the height here to be c log n levels. Yep, right here. So I seem to have, oh okay, yeah. So now we analyze the coin flipping part of this particular experiment. So we see that we analyze it, and we assume that we have a coin. It's a balanced coin, so the probability of heads is half and tails is also half. Surprise, surprise. Now we claim that the number of flips till c log n heads is in theta log n with high probability again. So we make an assumption, say we have k times c log n flips. Now the probability that we have exactly c log n heads is, again, so this is fairly easy. We have so this particular thing represents a combination, that is, out of the k c log n flips, we need c log n heads. So this is k c log n c log n. We are using combinatorics here, and we multiplied with the chances of c log n heads coming up and the chances of k minus 1 c log n tails coming up. So I think that's pretty clear now. But we don't want exactly c log n heads. What we are interested in is at most c log n heads, which is the probability that we don't get C log n heads. So that is the opposite of what we are claiming, right? So the probability of that we have at most C log n heads here is again, so this is an overestimate now, and we have completely dropped the heads term that we were looking for here. So now we have a purely tails term because we're talking about at most C log n heads, and this term, the combination of k from choosing from k log n, we choose C log n. This is an overestimate now because we are less than C log n now. So we use this fun fact that ycx, that is y choose x, is less than equal to e times y by x to the power x. So again, substituting it here, we write this. So it's e to the k, e times k C log n upon C log n. So you can see that this will cancel right out to the C log n. Again, we are simply using this substitution times the tails. So again, just copy pasting the tails term. Now we simplify this a little, so we cancel it. So we simply have k times e whole to the power C log n times half to the power k minus 1 C log n. Again, this will require some mathematical gymnastics that are not particularly complicated. So with this is, since we have we have chosen a balanced coin, so p is half, so we simply take this into the exponent. So we have 2 to the log ke minus k plus 1 C log n, and this is the bound on the probability that we are looking for. Again, we choose this term to be alpha minus alpha, it's explained right here, and when we choose it to be minus alpha and take the 2 to the exponent, we get 1 by n to the alpha, which is what we wanted. So as we can see, as k tends to infinity, so here's what we wanted to do. We claim that we'll get at most C log n heads, and we introduced a seemingly random parameter k over here, and now we have shown that as k tends to infinity, so you can see that as this tends to infinity, so k increases a lot more than log k. So we see that as k tends to infinity, alpha will also tend to infinity, and for all c, regardless of what c we have. So we have shown that this result, that C log n heads, number of flips till C log n heads, is theta log n with high probability, and since we have shown it bounded by or an error term of order 1 to the n alpha, we have finally shown that this is indeed bounded in theta log n as was claimed. Let's see how much time we have. So we are almost out of time. Just one last thing, I recommend a few references. So I'll be the first one is actually a thesis, 1993 thesis from the University of Canada, as far as I remember. Yeah, so this is pretty involved and there are much more tighter bounds. So if you really want to explore what skip lists are all about and you're really enthusiastic about them, I highly recommend this reference. This particular slides, my treatment of the complexity analysis of skip lists was largely taken from Eric D. Demain's open course, MIT open course slides. So the links are right here. Again, you can click on these links. They hopefully will be in the description below. And these slides, the final slides titled Analysis of Algorithms, were used to introduce the algorithms, and so that is where we got the diagrams. So I highly recommend that you read these particular, especially I'll recommend this Introduction to Algorithms, MIT open course. This is very informative and this made things very clear for me. Thank you very much.